Welcome. We are just finishing up the notes that we started yesterday. And for two of my classes, we didn't get to this example, so I have you linked to see this entire video where we can see example 1. And for my other two classes, you should have been linked to where we start on the next page. But if you ended up at this video, it's okay. Just fast forward through this example. So our example here, we have 3 different drawings, and we're going to determine if each one is a polygon. Now the first one, the one on the left, does have some angles. So there's an angle here and an angle there, but it's not a polygon because it's not closed. Remember, our characteristics of a polygon is that it is a closed shape with many angles. That's what that polygon word meant. This middle one, this is a polygon. So it's closed shape. We can see that if we start drawing at one end, we will eventually, and here's the super messy version, eventually close back up. We'll get back to that start. And inside, we do see many angles. Now it looks like it has polka dots. So this is a polygon, yes. Now if we're going to check and see what we would call this polygon, we can count the angles. So if you were following along with my little half circles, they were a little weird. It was hard to see them. So let's try this. There's one angle there. There's an angle. There's an angle. That's 4, 5, 6, 7, 8, 9, 10. So there's 10 angles here. If you're counting sides, the number of sides and the number of angles are going to match. So you could count the sides. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Either way, there's 10 sides, 10 angles. So we would call this a decagon. Then the next one, that one is not a polygon. It's closed, but it doesn't have any angles. And the word polygon literally means many angles. So circles, while we will study circles, and there's a lot that we can do with circles, they are not polygons. So we're going to study them a little bit differently. So that gets us all caught up with everyone else. So now we will move to part 2, where we turn the page over and fill in some things with angles. All right, here we are ready for part 2 of our notes about polygons. So this is the back of the page that we started yesterday. So remember, this was the page we started yesterday with all the shape names. And now we're on the back side of it. We're going to talk about interior angle measurements in polygons. So just like triangles had a predictable sum when you added up the 3 angles, they always add up to 180. The polygons are going to be predictable also. So we will remind ourselves triangles, the interior angles always add up to 180 degrees. It's kind of an important math rule that we need to remember. So that's why I'm repeating it over and over and over. So then the question here, do you think the interior angles of other polygons will add up to the same thing or more? And a couple of the classes yesterday actually mentioned this and started talking about this. So pause the video for a second. I want you to think about this and write your own answer first, and then come back and we'll see what we can decide together. All right, as you were thinking about this, the interior angles of other polygons, you may have thought of a specific example like we're going to do in example 2. We're going to think of a specific actual polygon where you know. But, spoiler alert, the interior angles will not add up to 180 unless it's a triangle. So only triangles have 180. Other polygons have other sums. But they will be predictable based on the actual shape we're looking at. If it's a 4-sided shape or a 5-sided shape or a 6-sided shape, once we see how many sides there are and what that shape looks like, we will be able to predict what the sum should be. So for example 2, I do want you to pause the video again. Think of a non-triangle polygon. So any closed shape with straight sides where you already know what the interior angles are supposed to be. Now, it seems like a strange request, I know, but there is at least one shape that everyone's familiar with that you know for sure what the interior angles are. So pause the video and then we'll see what we get. Okay, hopefully you actually paused the video and took some time to think about maybe a shape that you know. And I know of a shape called a rectangle. You may have gone with square. But a rectangle, I know, has 90-degree angles in every single corner. So this next question, once you decide on a polygon, what are the angles? They're 90-degree angles. So we have 4 90-degree angles. So if I were going to add those up, if I have 90 plus 90 plus 90 plus 90, that equals 360. Now, I did say these were predictable sums. So just like every single triangle adds up to 180 degrees, every single four-sided shape, not just rectangles, but every single four-sided polygon is going to have that interior angle sum of 360. So we'll put a little note here. Any quadrilateral, remember that was the name for four-sided shape, and we're going to call this an interior angle sum of 360 degrees. So we don't really call that the quadrilateral sum theorem or anything like we have the triangle sum theorem, but we actually can find this and we can prove this for any polygon using the triangle sum theorem and using triangles. So that's what we're going to move towards next. This next part, we can predict the sum of interior angles of a polygon by drawing triangles inside of it using a part of the shape called the diagonals. So the diagonals of a shape connect corners to non-adjacent corners. Now, non-adjacent, I means not right next to. They're not neighbors. Because what happens if you go from one corner to its neighbor, you've just drawn a side. Like you've just traced the side of the shape, and that's not what we want. We want diagonals that actually go across the shape. So here's what we're going to do. We're going to start with the polygon you thought of above. We're going to go with the rectangle here. We're going to draw it nice and big, though. Oh, I thought it would fix it for me. There we go. Okay, we've got a nice big rectangle. So I know in a rectangle, we have 4 90-degree angles. So a rectangle, you know, that's pretty predictable. But if I had drawn a rhombus, those angles are not as predictable. They can be pretty much anything as long as the opposite ones match. So if we're trying to predict what the sum is on a rhombus, we might not know. But I'm going to show you a way in this rectangle, since we already know we can use the 360 to verify. I'm going to show you a way you can check this for any shape. So these diagonals, you start at any corner. I'm going to pick this top left corner. And we're going to draw all the diagonals that we can. Number one rule, we don't want to cross any diagonals over each other. So we're going to make triangles. But don't cross diagonals. And you'll see what I mean when we get to bigger shapes. So if I draw diagonals from corner to non-adjacent corner. So if I start at this corner and go down here, that is an adjacent corner. We're not going to use that. That's just a side. That's not the diagonal at all. But if I come over to this corner, that's going to be a diagonal. And guess what? Most of you would call that a diagonal line anyway, right? You see that, you're like, oh, it's a diagonal line. But technically it is the diagonal of the shape also. Then let's check the other corner. But if I connect this corner out to that one, then, you know, we're just tracing the side. So I have now, just with that one diagonal line, now I have a triangle here. I have a triangle here. And I have a triangle here. So I cut my rectangle into two triangles. Now, if we look at the interior angles of these two triangles, so we've got one right here, that's a right angle. It matches the right angle that was already there. Then in that top corner, so let's just look at the green triangle right now, the one on the bottom. I've got this angle. It doesn't quite use up the full 90 for the rectangle, but that's okay. It's a triangle. It's not going to have two 90-degree angles. Then here's the other, that's the little angle in that triangle. So those three add up to 180 degrees because it's a triangle, and all the triangles add up to 180 degrees. Then we come to the other triangle. We've got this little angle, but guess what? If we use that angle and the green one, we've covered the entire 90 degrees. We've now included the entire 90-degree corner of the rectangle just by using these triangles. And over here, there's our third right angle. So we've got one that was covered originally here in the green triangle, one that combined from green and gray, and then one from the gray. We've covered three of our right angles so far. And then this third angle in our gray triangle over here, not quite the full 90, but if you include the green triangle there, we do cover the full 90. So all of our interior angles for the triangles add up to 180 degrees in each triangle. But we've also, when we put all those angles together, we've also made all of the interior angles for the rectangle. So when you do this, the goal is to cut your shape into triangles so that the triangle angles are the angles in that original shape. So now I know that the green angles all add up to 180. The gray/black angles all add up to 180. So if I want the total, I just add those together. There's two triangles, so I have 280s. And that's how we're going to show, with any shape, what the sum of the interior angles is supposed to be. Now, in this case, we knew it was supposed to be 360, but we've just proved it and proved that it's going to work really for any quadrilateral. If I come over to my rhombus on the left here, I divide that, I get two triangles. So this side is 180 degrees. This side's a triangle with 180 degrees. So a rhombus altogether would be 360 degrees. Even though they're not right angles, some of the angles are bigger, but the other angles balance out and become smaller so that the total is still 360 for a four-sided shape. So no matter what your four-sided shape is, you are always going to add up to 360. Now, we can do this triangle thing with any polygon. So a hexagon is nice and straightforward because what we can do, since there's not really any craziness, this is a convex polygon. Those are the easier ones to do this triangle method with. What we do, we pick one vertex. I'm going to pick that top left again. I like the top left. Now again, we're not going to use this one because that's just a side. But if we come down here, there's a diagonal because we went from corner to corner, right? And we can come down here, that's corner to corner. From here is corner to corner. And then this one, corner to corner, that's just a side. We're not going to use that one. So when we look at the actual triangles that we made, there's one here, there's a second one, a third one, and a fourth one. So we have four triangles. Each of those triangles, first off, each of those triangles does have its interior angles in the corners of the hexagon. What you don't want are these triangles happening in the center. We want all of these triangle edges, all of those angles to be out at the edge of the shape. but each has 180 degrees. So our total for the hexagon, so hexagon total, whatever 4 times 180 is. Let's see if I have a calculator available here. Nope, haven't used it in a while. 4 times 180, so let's stack this up so I can do this. 4 times 0 is 4. 4 times 8 is 30. 4 times 0 is not 4. 4 times 0 is 0. 4 times 8 is 32, so 720. So since we can fit those four triangles, 1, 2, 3, 4 triangles into a hexagon, each of those triangles includes 180 degrees of interior angle measurements. We just multiply that number by 4, and we get the total for interior angles of a hexagon. And again, that's consistent. This is a very nice, open, regular hexagon is what we call it. It's got 720 degrees. But guess what? If I drew one of our crazy hexagons, like the, in 7th period, we drew the military chevron, like the bars you get when you get promoted. That's a terrible one. But that's a 6-sided shape, again, so that's a hexagon. So its interior angle sum would be 720 degrees also, even though it looks so different than the hexagon we originally tried it on. So I'm not asking you guys to memorize all those numbers. Like, I don't need you to memorize that a square or that a quadrilateral has 360 degrees inside of it. I don't need you to memorize that a hexagon has 720. I would love for you to understand this concept, so anytime I give you a shape, you can approach it with these triangles and then figure out what the angles should be. If you haven't noticed, I'm not real big on memorization. I'm big on the figuring out. So now the star is kind of a challenge problem. It's a little different because if you notice, we can't just pick one vertex, one of these corners, and make it to everything. So obviously that's the adjacent one. We wouldn't use that anyway. But out here, if we go there, that's not even inside the shape. That's not interior angles, that's outside. So the star's a little different. If you're up for the challenge, please continue with us. If you want to skip this challenge and move straight to the examples, you're welcome to. I would completely understand if you fast forward through this challenge example. Okay. For those of you who are staying, thank you. That's awesome that you like the challenge. So this, remember from the example 1 on the last part of our notes, this 5-pointed star is actually a decagon. So the nice thing, if we do use our triangle trick to determine how many interior angle degrees this should have, that's going to be the same for any decagon. So it's kind of nice to be able to run through that. But remember, the trick is triangles. We're looking for create triangles with diagonals. We're going to use diagonals to create the triangles. But there was another thing we needed to notice. We don't cross diagonals. Because what happens if you cross diagonals, like let's say, don't copy this down. I'll put it in dotted lines even, so you remember not to write it down. If I do one diagonal here, and then I do one diagonal here, I have actually not made any triangles. I made a quadrilateral over here, but its interior angle is here in the center of the star, and that's not what we want. Remember what we're trying for. We're trying to get triangles so that we can measure all of these interior angles. We want triangles so that the triangle corners actually line up in one of those arcs. So all three, every time you make a triangle, each of the 3 angles should be in one of those little spots. Now I think I'm going to erase that, and maybe I just highlight each of the angles, and that's where that's our goal. I'll highlight them with the gray. So any triangle we make should have its 3 corners in 3 of these 10 spots. Now you can get creative with your triangle making, and that's totally fine as long as you don't cross your diagonals. So the easiest way to start making triangles in a star, and really before I do this, I would love for you to pause the video and try to make all the triangles yourself. So go ahead and pause. See if you can make the triangles, see how many there are, and then come back and you can see how I decided to make my triangles. All right, welcome back. I really do hope that you paused and started to make triangles. The easiest way to start, honestly, is to just cut off all the points. So if I come in here and I use the diagonals, they're non-adjacent, right? Because the adjacent ones, if I started here, whoops, I thought I changed colors, and went adjacent, it would go out to the point, and that's not the one I'm using. So I skipped a vertex and just cut across. So I now have 1, 2, 3, 4, 5 triangles. So there's 5 so far. We'll write in 1, 2, 3, 4, 5. But this inside part, I want to make sure you see this. I still have parts of the angles that we need that aren't accounted for. Some of those gray circles are not in triangles yet. But this center shape, I actually just made a pentagon inside my star. But now we can keep the diagonal idea going, and I can actually make diagonals in that pentagon to make more triangles. So there's a diagonal in the pentagon, and there's a diagonal in the pentagon. So now I have 1, 2, 3 triangles there. So we had 5, there's number 6, number 7, and number 8. So we ended up with 8 triangles. Now remember, the whole point of this was not just to make a fun, cute picture. The whole point of this was to remember that each of those has 180 degrees for its interior angles. So if we want to know the interior angles of a decagon and what they should add up to, we're going to take 8 times 180. 8 times 8 is 64. 8 times 1 is 8, plus 6 is 14. So our decagon interior angle total, or angle sum, we'll keep with the same official words, 1,440 degrees. That was supposed to be a 0 and then degrees. So there you go. So be flexible with your triangles, but remember those first 2 rules. You're using diagonals, so you're always starting at a corner, ending at a corner, and you don't want to cross the diagonals. Otherwise, you're going to start some of those angles in the middle instead of out around the original shape's edge. So if you stuck with me through that challenge problem, then thank you so much. But now we're going to get to the examples. Okay, in example 3. We're going to use what we know about the sums of interior angles to find the missing measure. So this is just like we did with the triangles, but instead of always having 180 degrees and subtracting off what we know, we have to find out what the sum is supposed to be first, and then we'll subtract off from that. So if we look at this one, now we could count up the sides. There's 1, 2, 3, 4, 5 sides. So if you've already done a problem that had a pentagon in it and you already know how much the 5-sided angles should add up to, then you're good. You can just start with that. But we didn't do 5. So we're going to look at our diagonals. Now, if we're trying to cut this into triangles, remember you can be flexible. We don't always have to start at the top left, and maybe actually the top left is not a good place to start. But remember, our goal is to create triangles. So one of the things I see that I can do is if I make this diagonal, now I have this as a triangle. Okay, so that's one triangle. Now, right here didn't quite line up. This doesn't quite line up with this. So this is not a triangle right now. This is still a quadrilateral over here. But if I do the same thing, go from that center point out to the right angle, then guess what? I have a triangle here and a triangle here. So we have 3 triangles, each with 180 degrees. So our pentagon total will be whatever 3 times 180 is. So 180 times 3, 0, 3 times 24. 3 times 1 is 3, plus 2 is 5. So pentagons, $540. Now, that is not our answer. This is like when we had our triangle problems from the other homework the other day, and we knew we always started with 180, and then we subtracted. Now we know that for this problem, we're starting with 540. So now separately, there's 5 total angles. So if you wanted to write out a full official equation, like we did in the notes for the triangles, you're going to write out 5 things, 1 to represent each of the angles, and the sum of all of those is 540. So let's look and see what we have. In that pink triangle, I see a 38, so I'll put 38. Then if I go above that, there are 2 90 degrees. They're not in one single triangle, but there are 2 boxes. I do see an X in the yellow triangle, and then there's a 282 in the orange one. Let's write that a little bit better. 282. So now that we've got our full equation written out, I'm going to go ahead and combine some like terms. So my X is going to stay X. There's no other X's to match with it. But I am going to be able to combine 38, 90, 90, and 282. So if you want to use a calculator, give me just a second. I'm going to open up my calculator. This is the Desmos graphing calculator. You have it on your iPad right now, and you are welcome to use it if you don't have a side calculator. So I know there are other calculators you can look up, but this is an app that you don't need the internet for. So if you're Wi-Fi-less at some point, you can still use this calculator. And it's a really fantastic calculator. It's my personal favorite that I actually use when I have to do math problems. So 38 plus 90 plus 90 plus 282. Our like terms come up to 500. So x plus 500 does have to equal 540. And many of you will see where we're going already with this, but we're going to subtract 500 from both sides. And we're left with x equals 40. So there you go. That was solving the problem. So you can see how closely our process matches with our triangle problems. We just have a bigger number, and that number could change based on the shape that you're working on. So any pentagon would be 540. But when we go look at our next example, it's a quadrilateral. 4 sides instead of 5. So we're not going to have 540 anymore. It'll be a different total. But then the rest of our process was the same. Find out all the angles you know, subtract those off from the total, and you're left with whatever the missing one was. All right, then here's our last example. It is a quadrilateral, and you might remember from our earlier notes and earlier exploration of this system that we do have a total we're going to use. I'm going to show just with the diagonal again. So when I use diagonals, I can cut this into 2 triangles pretty easily. So 2 triangles times 180 degrees each. equals 360 degrees for quadrilaterals. So remember, that is not our final answer. That's just giving us our starting point. So now that we know it's 360 though, honestly, most of you are going to start with 360 and you're going to subtract off what we know. Minus 75, minus 110, minus 115. Whatever you get here, that will be your answer, and that's okay. Now, I do prefer the full equation method because if we end up with some algebra in these angles, instead of 115, maybe it says x plus 35. You're not going to be able to just subtract x plus 35 off of 360. So I do really want you to get in the habit, I want you to try and get in the habit of writing out writing out whatever it says for your 4 angles, writing an equation where that equals your interior angle sum, which remember changes based on the number of sides that your shape has. But now we have some like terms here. I'm going to bring my calculator back in. I don't know where it went, but okay, 110 plus 115 plus 75. So 300 plus x equals 360. And we got another one where the subtraction's easy. That's nice. So we'll subtract 300 from both sides, and our x will equal 60 degrees. That's the angle that we're missing. Oops. All right. So hopefully that helps you get started on your assignment. I will tell you that in your homework, we're focusing mostly on quadrilaterals. So you may not have to do the diagonals, count the triangles trick very often, because if we're focusing on quadrilaterals, then you'll start to realize that we're just going to use 360 over and over and over. But there you go. That's it for our examples. Thanks for bearing with me through some video notes. In the future, just so you know, if we do this as a planned thing, I generally cut the videos into smaller chunks. I know this was one long chunk, but hopefully you paused and took a break whenever you needed to so that you were able to get all the information. Hopefully you understand things. Feel free to send me emails if you don't understand what's happening, or I will be back in class with you on Friday, and you can ask me your questions then as well. So thanks for sticking with me through this video, and I'll see you guys soon.